Welcome back, fellow mitochondriacs, to another episode of Cancer as a Mitochondrial Metabolic Disease. What if one of the biggest advantages cancer cells have isn't a specific gene mutation, but their environment? Most people think cancer cells are just growing out of control, but many tumors grow in a super low oxygen environment. And that lack of oxygen actually triggers survival mechanisms that help them evade the immune system and rewire their metabolism. Today, we are going to continue to explore tumor hypoxia or low oxygen and why this matters so much. So without further ado, let's get into it. So because the oxygen status of the tumor is so critical for therapies to work and why there is a lack of response to therapy sometimes, I broke this into 4 parts, and this is going to be part 2. We're going to start by looking at a very key regulator of this whole process called HIF-1. And this paper was published in May of 2021 and is titled Cancer Cell Metabolism and Hypoxia, Role of HIF-1 as a Key Regulator and Therapeutic Target. And it says here, hypoxia-inducible factor, HIF-1, is a pivotal modulator of the metabolic reprogramming, which takes place in hypoxic cancer cells. In the hub of cellular bioenergetics, mitochondria are key players in regulating cellular energy. Therefore, a close crosstalk between mitochondria and HIF-1 underlies the metabolic and functional changes in cancer cells. And I like this graphic because it kind of illustrates what's happening under kind of normal conditions versus hypoxic or pseudohypoxic conditions. So we have a graph here of oxygen. So this is like maximal amount of oxygen getting to the tissues. And then we go down until we get into the hypoxic ranges or even anoxic ranges, which is low oxygen and then even no or very little oxygen. And under normoxic conditions, normal oxygen or physioxia, this protein HIF-1 is continually being made, but it's also continually being degraded. And so when there's hypoxia or pseudohypoxia, which we'll get into, when we have hypoxia, then hypoxia factors are not being broken down. They're being stabilized, and those hypoxia factors will then go to the nucleus of the cell, and then there'll be hypoxia response elements or HREs that then control different things that happen downstream of that. But HIF-1 is a big, big player. And then this is just like another graphic here. So here's normoxia. The HIF-1 is being shuttled to the proteasome for degradation continuously. And then if there's hypoxia, then those chaperone proteins will then be released, and hypoxia factor will not get broken down by the proteasome. It will then go to the nucleus and it will change gene expression. And we'll look at all the things that it can do. But it, needless to say, is a very critical player for the metabolic reprogramming that happens within cancer. And then this is just a very, very short list here, but hydrogen peroxide, succinate, fumarate, and L2HG are some of the pseudohypoxic factors where basically these things and other things, pseudohypoxic factors, can stabilize hypoxia-inducible factors without needing to have true hypoxia or low oxygen and have a very similar process. So here is another graphic, hypoxia, HIFs right here, hypoxia-inducible factors. I also put here pseudohypoxia. We'll go over that in the future. And here we have, it regulates metabolism, angiogenesis, or the making of new blood vessels, the EMT, cancer stem cells, migration, invasion, tumor acidosis, and pH, the inflammatory environment as well. And all of this leads to tumor progression. One of the ways that the metabolic reprogramming actually happens because of HIF is because it has profound effects at the level of mitochondria. So it says here, HIF-1, a big chapter in the Cancer Tale, published in March of 2016, and it says, many HIF-1α mediated biological effects are beneficial for tumor progression, including metabolic shifts towards glycolysis, or the Warburg effect, inhibition of fatty acid beta oxidation, production of cellular reactive oxygen species, and altering expression of tumor suppressor genes. HIF-1 promotes selective mitochondrial autophagy, resistance to cell-mediated lysis of cancer cells, induction of pluripotent cancer stem cells, and epithelial mesenchymal endothelial transitions, beneficial for tumor growth and progression, loss of E cadherin. So one of the reasons I picked this particular publication is because it shows that HIF-1, when it's stabilized, when it's allowed to kind of roam free, not only does it change gene expression to metabolically reprogram the cancer cells, it will directly, in multiple ways, shut down mitochondrial energy production. It will shut down the conversion of pyruvate to acetyl-CoA through an enzyme called PDK. It will shut down the electron transport chain directly. And as it says here, it will promote selective mitochondrial autophagy or mitophagy. So when HIF is stabilized under hypoxic or pseudohypoxic conditions, that will lead to excess mitophagy, which will get rid of mitochondria. Not only will it shut down their metabolism, but it will actually get rid of excess mitochondria. And that will gradually lead that cancer cell to rely more and more on glycolysis because there's no mitochondrial mass or energy production happening. So it's like a compensatory mechanism towards glycolysis or the Warburg effect. And then it also directly leads to metabolic reprogramming. So a lot of the things that it does at the level of the genes. So if we go back to this here, so at the level of genes, it's going to actually lead to metabolic changes by upregulating and expressing more proteins that are responsible for the metabolism of glucose and glutamine, the primary fuels of cancer. So we see here, everywhere there's a black lightning bolt, that means that is upregulating that particular protein in the glycolysis system, right? Here's glucose transporters, here's lactate transporters, here's all of the glycolytic enzymes, and here's lactate dehydrogenase enzyme, right? And then the red lightning bolt is induced by HIF-2α, and that is also a hypoxia factor, and it's going to be responsible for the glutamine side of things. So here's glutamine transporters, here's glutaminase enzyme, glutamine dehydrogenase, and then also a byproduct of glutamine metabolism is the fatty acid synthesis from citrate. So that's also upregulated by HIF-1α. And so we see here, we have normoxia, right? Here's normal oxygen. And I wish it kind of had a little more detail here because it'd maybe give us what the partial pressure of oxygen is in millimeters of mercury or percent oxygen, but this is the graphic we got. So as you can see here, as we go down on the ladder of normoxia to mild hypoxia to severe to straight up anoxia or no oxygen at all, you're going to see metabolic changes happening here. And you're going to see here that glycolysis is increasing, OXPHOS is being shut down. Here's OXPHOS being blocked or shut down. And there may be some compensatory mechanisms as a survival to try to get OXPHOS to be upregulated. But the problem is that even if OXPHOS was able to be upregulated by PPD3 here, then the lack of oxygen would make that OXPHOS is actually not working, which kind of makes this graphic a little bit confusing because here it is like OXPHOS is being decreased. Here's OXPHOS that's actually being shut down because there's no oxygen for it to happen and because of hypoxia factors at play here. But there's other compensatory mechanisms like P53, which are trying to do the opposite things. But because there's low oxygen, there is no ability for OXPHOS to happen, even if there were secondary compensatory mechanisms to try to make it actually work. And as we looked at in the prior video, even mild amounts of hypoxia is going to decrease the efficiency of OXPHOS. And when we get to severe and anoxia, that's when there's little or even no OXPHOS happening whatsoever, just from the oxygen perspective, not even looking at other mechanisms with HIF-1α. And so it just goes to show that even if Seyfried was completely off and he was completely wrong about mitochondria being damaged and there is no mitochondrial defects to structure, number, and function of mitochondria, just hypoxia by itself would lead to OXPHOS failure and the inability to metabolize for fuel, fat, ketones, other amino acids, etc. Because you need to have not only functioning mitochondria, but you need oxygen for that to happen as well. And so there's just a double whammy against that being a real contributor. And I think it really is irritating to me because in the literature, it'll say, oh, these cancer stem cells, which are in the most hypoxic, poorly vascularized regions of the tumors are using OXPHOS, are highly adaptable, et cetera, which doesn't make sense from a variety of ways when you actually analyze it logically. So I want to start to paint the picture of how hypoxia not only reprograms cancer cells, not only leads to tumor progression, but also leads to treatment failure. And so this is a paper that was published in October of 2024 and it's titled Targeting Hypoxia with Nanoparticle-Based Therapies, Challenges, Opportunities, and Clinical Implications. And it says here, hypoxia is a crucial factor in tumor biology, affecting various solid tumors to different extents. Its influence spans both early and advanced stages of cancer, altering cellular functions and promoting resistance to therapy. Hypoxia reduces the effectiveness of radiotherapy, chemotherapy, and immunotherapy, making it a target for improving therapeutic outcomes. And in the paper, it says here that cancer has become a global public concern due to aging of the global population, complex treatments, and massive economic burden. Chemotherapy is the most preferable approach for mainstream medicine for cancer alone or in conjunction with other treatment options like immunotherapy, photodynamic therapy, photothermal therapy, radiotherapy, etc. Radiation therapy is an integral part of cancer therapy, and radiosensitivity of tumor tissue depends on the tissue oxygen tension or the amount of oxygen in the tissue. This is why radiologists primarily focus on the distribution of oxygen partial pressure in tumor tissues. Hypoxia represents a significant physiological stressor characterized by an inadequate oxygen supply to specific regions or organs, surpassing their regular demand within the tumor microenvironment. This phenomenon is particularly relevant in cancerous tissues, notably solid tumors. We'll also see that not solid tumors also have this problem as well. Under normal circumstances, tissue oxygen tensions range between 24 and 66 millimeters of mercury. However, this tension plummets drastically below 10 millimeters of mercury in hypoxic conditions. Oxygen plays a crucial role in stabilizing DNA damaging free radicals that are induced by radiation. Cancer cells exhibited heightened resistance to radiation therapy in its absence, necessitating higher doses than usual for effective destruction. Moreover, hypoxia diminishes the sensitivity of cancer cells to chemotherapy and immunotherapy during treatment. Notably, the presence of hypoxia within the tumor microenvironment not only fosters metastases, but also confers resistance to reactive oxygen species generated cancer therapies. On the other hand, hypoxia-inducible factor HIF-1α promotes vascular endothelial growth factor, VEGF, production through HIF-1 signaling pathway, resulting in the production of blood vessels. However, this elevated blood circulation cannot fulfill the requirements for a progressed tumor. In such a situation, the tumor cell sustains due to transformation of glucose metabolism pathway, which again is upregulated by HIF-1 pathway. This HIF-1 is a big deal. Tumor hypoxia, from basic knowledge to therapeutic implications, published in January of 2023. It says, in addition, emerging evidence suggests that limited efficacy or the development of resistance towards anti-tumor therapy may largely be due to hypoxic TME or tumor microenvironment. And this graphic is actually pretty cool because you'll see here, here's the hypoxic TME tumor microenvironment. Here's HIF kind of everywhere, right? And then it's going to show all the things that hypoxia and hypoxia-inducible factors, as well as other oncometabolites, which we'll talk about, can actually have an effect on. So here's T cell blockade, and here's the PD-L1 and CTLA4. These are the tumor evasion immune checkpoints. Here's VEGF or vascular endothelial growth factors. Here's suppressing NK cells, suppressing and shifting macrophages from M2 to M1. Here's the blockade of dendritic cells, which are antigen presenting cells. And then of course, what we look at mostly on this channel is the metabolic dysregulation of both glucose, glutamine, lactate, succinate, etc., which are all oncometabolites, which we'll look at. Here's another paper titled Hypoxic Tumor Microenvironment, Destroyer of Natural Killer Cell Function, published in April 2024. And it's just looking at how hypoxia leads to all of these problems. Here we go. Invasion, EMT, angiogenesis, metabolic reprogram, treatment resistance, that's chemo, radiation, and immunotherapy, immune escape, epigenetic reprogramming, metastases, and progression of disease. And I'm going to culminate our understanding of how hypoxia can lead to treatment failure as kind of a general gestalt with this paper here. Older paper, October of 2014, but it looks at how there's a relationship between tumor hypoxia, prognosis, and therapy failure. And we've seen a graphic very similar to this, right? Hypoxia or pseudohypoxia, and then that leading to the hypoxic response element activation and target gene expression, which then leads to all those things we looked at in other videos. I kind of like this graphic a little bit because you see how it says activation by growth factors, PI3K, AKT, mTOR. If you know anything about these growth factor pathways, they pretty much all work through these same kind of like pathways. So your HER2s, your androgen receptors, insulin-like growth factors, et cetera, EGFRs, they pretty much all work through these same pathways, right? And what do? They will then lead to hypoxia, inducible factors being stabilized. And so these are all also pseudohypoxic factors, right? So hyperglycemia is just one way that these can be stimulated, and then that can lead to hypoxia inducible factor stabilization, right? So what I'm trying to get at is that there's many ways that hypoxia inducible factors can be stabilized, even if there is no hypoxia at all, right? Those are called pseudohypoxic factors. And we can look at those further in the future. So I specifically brought this up because of these tables that this has, right? So here we go. Pathophysiology of hypoxia under the clinical importance of tumor hypoxia. And it says hypoxia is a pathophysiological property that is defined as a state of depressed oxygen tension. Hypoxia can be present in tissues, including tumors, causing the impairment of cellular or organ functions once critical oxygen levels are breached. Localized tissue hypoxia as it relates to tumors can be a result of two types of oxygen starvation. Two general types of oxygen starvation. Hypoxia can be perfusion limited, acute hypoxia, caused by a temporary reduction in blood supply. Alternatively, hypoxia can be diffusion limited, chronic hypoxia, caused by insufficient vascularization, impairing the metabolic needs of the growing tumor. The presence of hypoxia in cancerous tissues was first reported by Tomlinson and Gray, who observed that hypoxic yet viable lung carcinoma rods were surrounded by necrotic core caused by a tissue oxygen gradient. All types of solid tumors, especially malignant solid tumors, are subject to hypoxia, often exhibiting oxygenation levels measurably lower than that of their tissue of origin. Recurring tumors often exhibit a higher hypoxic fraction than primary tumors. A tumor's hypoxic status cannot be accurately determined anatomically, as the presence of tumor hypoxia is independent of the tumor size, stage, grade, or histology. Intratumoral oxygenation often disperses heterogeneously, and therefore an accurate characterization of tumor hypoxia is possible only from composite measurements. So we've seen a table that looks very similar to this. So this is millimeters of mercury, not percent oxygen, right? And here's the tissue of origin, right? So as we looked at before, generally it's like somewhere between like 30 and 40. This table is showing that some of these tissues of origin can be as high as 60 to 70 millimeters of mercury, depending on the location, right? And then we look at the average of the tumor, right? So here is a tumor, head, neck, 10 millimeters mercury, 16, slightly more, probably because it's directly related to air gas exchange, right? Breast 10, pancreatic 2, cervical 9. The bottom line is if we look at all of the averages, it's generally about 10 millimeters of mercury. So that's somewhere between 3 to even as high as 6 to 7 times less oxygen in that tumor than normal tissues. This is critical. And then we look at outcomes, right? Here's decreased survival, biochemical failure, decreased survival, all the way down here. It's a prognostic factor for all kinds of types of tumors here. And then here's an example where if a person had a PO2 in their tumor of 20, which is pretty high for a cancer since the average is 10, they would be complete responders to the standard of care. But if they had lower amounts of oxygen in that tumor, if they were slightly below the average, which is about 10 to, let's say it's 4.7 plus or minus 3, they were complete non-responders. Same tumor, different oxygen amounts, and either complete responders or complete non-responders. So oxygen status is critical for even the standard of care. And that's something that I think that we can have a big effect on with minimal cost and equipment needed to affect this, which will dovetail nicely into our discussions about normobaric and hyperbaric oxygen therapy when we get to actual like treatments in the future. If you like videos like this, please like, share, and subscribe. And until next time.